Okay, let's come back to something else that I think is kind of neat. Shh. I want to come back to something that's kind of neat. And this is just a neat aside. Yep. Neat things to notice in orbital motion. I want to notice this neat thing, okay? And I want to go back to a definition that we said once before. Once before, we said that the period of orbit for something is really going to be equal to 2 pi r divided by 2 pi r divided by the orbital speed. And all we're really kind of saying is we're going to break down the analogy that it's kind of like linear motion, only in a circle. Okay, you know, like in a circle you say that delta t is equal to delta d over v. Well, in circles, sorry, this isn't a straight line. In circles, we're going around a distance, the circumference, divided by v, and that's period. Okay, so that's kind of a definition that we came up with before. And we just said a minute ago that orbital speed for a circular orbit is g capital M for the central mass over r all square rooted. So two things that I want to pull together. Okay? Now instead of saying v here, I want to sub in this expression. So I'm going to say that period is equal to 2 pi r over the square root of g m over r. You know, anytime you divide by a fraction, you're going to invert and multiply. So 2 pi r times the square root of gm. Invert and multiply the square root. Okay? And you can do that. Now, if I want to look at this in terms of, I don't know, like a non-square rooted function, what I'm going to do at this point is I'm going to square both sides. So period squared is equal to 4 pi squared r squared times, and I've squared the whole of both sides, so r over gm. Okay, and I'm not telling you why I'm going where I'm going. This is a neat thing. Okay. I say it's neat. You may not say it's neat by the time we're done, but I say it's neat. Okay? Now I want to simplify it one step more. I want to say that period squared is equal to 4 pi squared times, now r cubed, because r squared times r, over gm. Doing a little bit of rearranging. I want to get r cubed and the period squared on the same side together, and I want to take everything else to the other side. Okay? So I'm going to say that r cubed over period squared, because I'm going to take the period squared over to the same side as the r cubed, is equal to gm over 4 pi squared. Now what I want you to notice, and this is what is kind of neat, for a given planet, does this side of the equal sign ever change? It's just got the mass of the planet built into it, doesn't it? So for every planet, isn't that value always going to be the same value? Regardless of what orbiting body we're talking about? So let's say that we're talking about Mars. Mars would have a certain radius, and Mars would have a certain orbital period. But the central mass isn't Mars. What's the central mass? The Sun. So this value would have a certain value, including the mass of the Sun in big G. When I talk about Earth, Earth's radius of orbit would be a certain value, and its period would be a certain value. But the right-hand side of the equal sign still involves what mass? Not the Earth's mass, the Sun. So it's kind of a neat idea. The neat idea is this. The radius, average orbital radius for a planet cubed divided by its average period of orbit squared is always equal to the same thing as long as it's within the same orbital system. Okay, so Pluto's orbital radius cubed divided by its orbital period squared is going to be equal to the same thing as Earth's orbital radius cubed divided by Earth's orbital period squared. This is actually isn't that kind of neat? Like for any planet in our solar system, this ratio is going to be the same. So if you know the orbital radius of Pluto, because you can see that using a telescope, you could figure out how long it takes to get around the sun.
Pluto's not a planet.
Oh, Pluto's not a planet. Well, it's an orbital body still. Give it a break. Come on. Yeah. Yeah, there's a proportionality there. Okay? And actually, let's give credit where credit's due. We actually call this Kepler's second law.
I'm confused. Wouldn't the mass change for every different...
Oh, no, this M is the central mass, the sun.
Oh. That makes sense. I knew that.
Okay, so Kepler's second law. And so people seem to always give the credit to Newton for like pretty much everything in all areas. Come on, he couldn't have done everything, right? This is Kepler's second law. This is a guy who is very, very meticulous, making lots of observations and coming up with some of these conclusions. But this is something that we can show very simply in the math. I think that's kind of neat. Maybe you don't, but I do.